we begin the class today. So I was waiting for people to join. See, I hope that like the people who have joined today, I see 79 people. So none of you are planning to drop the course, right? Because the window for dropping the course is it's going to close by tomorrow. I think tomorrow, day after tomorrow, right?
Yes, that's right.
Yes, sir, 23rd.
Okay. So is anybody still considering dropping the course? So I'll tell you why am I asking, but yeah, is there anybody? I think you have gotten enough flavor of how the course is going to be and all that, right? So is there anything, any concern that, or rather, information that you might want to know to take the decision? Because initially we started with some 100 people, now we have about 85, I think. Some 15 people have dropped, which is okay, fair. Uh, Anybody else considering dropping the course?
Hi, sir.
Hi.
I'm considering to drop because
Okay.
of personal reasons.
Okay, no problem. Yeah, but you still want to continue attending the classes? Yeah, so that is one thing that I wanted to ask you. So once you drop the course, would these ICANN people allow you to continue attend classes? Or would they just remove you from all groups?
Audit isn't allowed for us.
Audit isn't allowed, huh? Okay, I see. Okay, so except for Ms. Sharmila, right? Anybody else considering dropping the course? Okay, I'll take that as a no. Okay, so this I think then this is the final class trend that we have. So I need this because we need to plan the assignments right now. We can form the groups of three and also plan the exam. So the exam, the midterm exam, I'm planning to have it after two classes, which is today there is one class where I'll finish this GAN thing, and the next class we will look at the variational autoencoders. We'll start with VAEs. After that, we'll have the midterm exam. So that would be, I will tell you. Today is 24th, 25th. Yeah, 12th is the here, right? So we can have it on 10th of October if it's okay for you. It's a Thursday. Uh, we'll have it on 10th. Does that work for all of you? 10th of October?
Sir, timing? Sir, timing?
Yeah, timing we'll have to see something that works for all of you. Maybe 8:30 to 9:30, 8:30 to 10 in the night.
Sir, it doesn't. Final date for submitting the first assignment, right? So normally we may extend till the day. So we may not have the time to prepare on 10th attempt.
Oh, I see.
And sir, one more thing, not sure, Thursday at this moment maybe, but it is office days for most of us, and many of us have actually the US client. I mean, not me, but many of my friends I can see in this class. So I don't know whether it will be a right time to take a exam for them.
Can we plan it on Sunday instead?
Sunday is also okay. So which means that we'll have to do it on 13th. So 12th is like Dashera. So 13th we should do. 13th October is okay with all of you. Anybody has a problem with 13th October?
So 13 works out.
13th is fine, huh?
Yes, sir.
So maybe what I'll do, no, I will write it here. Okay, so
morning
Sir,
should
but
be
please
better.
don't create a poll this time, sir. Don't create
no,
a
I
poll.
don't. I won't. I will just put it here. Midterm exam is on 13th Sunday between 10 and 11:30 a.m. Is that okay?
So can we have it on afternoon time frame, because people belongs to Christian and all will go to church in the morning times, including me. Is it possible afternoon Sunday? Yeah, perfect.
Okay, we can do afternoon. How about 2 to 3:30 on 13th? Anybody has problems with 2 to 3:30 on 13th of October? Okay, so if there are no problems, then we will freeze that time. I'm putting that on the WhatsApp group, okay? Okay, so no more discussions on this. Midterm exam is fixed on, yeah, we have to say 13th October.
And sir, sorry if I missed it. Any quizzes in between, or it will be direct 13th now for the
No, there
exam?
will be quizzes. I mean, see, quizzes are independent, right? Every fortnight there will be a quiz. So next quiz will be next Saturday.
Next Saturday. Okay.
So there will be a next quiz will be next Saturday. And yeah, so every alternative Saturdays we will have a quiz that is independent of this exam.
Okay. And what will be the syllabus, sir? I mean, from last quiz to next more classes, right? I mean, how many classes happened, or it will be total from day one?
For what?
Quiz.
Yeah, quiz will be cumulative, right? I mean, if some portion has been covered, the next part of the portion will be for the quiz. That's all.
Okay. I mean, from the day 0 till whatever covered, that will be quiz part, right? That means total 6 classes altogether.
And not
Yes.
day 0. I mean, like you can take
Okay.
it from like previous quiz to this class, right? So that way. Yeah, I
Okay.
should have said non-cumulative. Yeah, so it's just
Okay. Okay. Sure. Thank you.
yeah. Okay, so that is settled, I suppose. No more questions on that. Midterm exam is on 13th October between 2 and 3:30. So what I can do perhaps just block your calendars also. No, that would be a good thing to do. Let me do it right away so that all of us are going to do that.
And sir, this MCQ will be subjective or MCQ type? I mean, sorry, midterm will be MCQ or subjective type? I mean, just a pattern of the exam looking for.
It will be a written exam,
Okay. Okay.
subjective, not MCQ.
Okay. Sure. Thanks.
Calendar. Thirteenth, 2 p.m. What is the course number here? E1, E12860, is it?
Yes, sir.
Is it E1? I'm not getting this.
Sir, it's on the Teams it's on the Teams meeting top. You can see.
Add required additional. Add channel, okay.
Yes, sir. It's E1286.
Oh, correct. Okay. How do I make it a Teams meeting? It's not repeat. Yeah, I just sent a calendar invite. Can you all see that?
Yes, sir. Yes. Yes.
Okay, so great. So that is done now. It, can we
Sir,
get
it
practice
says,
problems?
yeah, sorry, it says DGM quiz, sir. Is it what we meant? Midterm, right?
Oh God. Can't edit it for some reason. Yeah, that is what it is. It should be, yeah. It midterm exam. Ain't it? Okay, fine. So practice questions. Well, see, this being a graduate level course, right? It's not a probability theory course or anything. So I can't give you practice questions that way. So what I would encourage you to do is read the previous year's notes and also the original papers of things that we are covering. Okay, it will be around that. And also you should, it would be proctored, so you need to keep your cameras on and then write the exam. Okay.
Yeah.
And the way to do it is either you write it on a sheet of paper, scan it and upload, or you can write it on your like iPad or whatever, and then share with us the PDF. Okay.
So notes can be referred, right? Or it's not?
You mean during the exam? No. If you want an
okay.
open book exam, I'll have to make it more difficult. If you want that, because I'll have to assume that you'll have access to notes and have to ensure that I should ask you things that are not there in the notes, right? So which means that it has to be made a little difficult.
Sir, maybe this question is not right to ask, but just asking, will there be a question that where we have to derive these formulas and all which you are teaching us?
Yes.
Okay.
I don't know how to answer it. Yeah, of course, you are supposed to know all that, right? So just,
Okay.
yeah. And I'll not ask you the exact thing, right? Because, whatever I've done in the class, I'll not ask you the exact thing, but something similar, something around it, right?
Yeah. I mean, definitely theory and all, definitely have to know, but these formulas and all like little tough to remember.
Don't have to remember anything, sir.
Okay.
It'll not be reasonable. I'll not ask you
Okay.
to remember anything other than some fundamentals, right? Like for instance,
Okay. Yeah.
see, you can't afford to forget the definition of, let's say, a density function, right?
No, that's for sure.
I'm saying there is some. Obviously, I would not ask you to remember some formula or something. I mean, you should trust
True.
me at that level with some reasonability to what we do.
Yeah. No. Thanks.
Right. Okay. Huh? Anything else? Any other comments on the exam stuff? Start with the class.
Sir, what about results for quiz 1?
I think that should have gotten right. I mean, immediately.
No, sir.
No.
No.
Really? Okay. So was it done on like it was not Microsoft Form, right? Microsoft Forms.
Google
It
or
is
Microsoft?
Microsoft, right?
Huh? Was it Google Form or Microsoft Form? I thought it was
Microsoft Form.
Microsoft Forms. No, hold on. Let me just ask Chandan. If there's some setting where you can make the outcome visible right after the quiz. Let me ask him to do that. Should be seen immediately, actually. Is not picking my call. Okay, I'll tell him to do that. Because generally the way I ask them to do it is once you submit your answers, no, you should get the marks, right? Because it is possible. Because it's a multi choice question type. Okay. Shall we
So
start?
one more question.
Yeah.
The Excel sheet that was passed to us to write the details of the assignment teams, it was having 4 columns, and we thought 4 people can join together and create a team. But you also told it's size of 3, so there is some confusion there.
I see. Okay. See, 4 is okay. Like, I mean, see, a recommended team size is 3. Okay. So if you see what happens is, no, if there are 4 people, then I mean, dividing work amongst 4 people will become too much. So I would recommend a team of 3. Okay. But if you are 4 people, then you should be aware of the fact that when we are grading the assignments, right, we will take that into consideration that it's a team of 4 and look for like more work.
Okay.
Yeah. Good that you reminded me of that. See, assignment, I hope that all of you have taken a look at the assignment. Okay. So what you need to submit is, as I've mentioned, there is one Jupyter notebook. So whatever has been given there as to do, right? That is the bare minimum thing that you should do. Okay. But that will not give you 100% marks. Okay. That will give you, let's say, 70 to 80% marks if you just do whatever has been asked for. Now, the remaining 30% will depend upon like what will be the observations that you would be doing, right? And what are the kind of experiments that you have done. Okay. And also I'm planning, I mean, this is not fixed yet. I'll have to ask TS if they can do it, but I'm planning to have a Viva, okay, for all the assignments combined. Sometime at the end of the course, we will have a Viva where we will ask you questions on the implementations that you have done, right, at the end of the course. Okay. So try to incorporate as much experimentations as possible and try out multiple ideas. And the total, I mean, evaluation depends on the quality and the quantity of the experiments that you have done. Okay. So yeah. So questions? Yeah, Arijit?
Sir, just a last question that this all assignments should be done in group, right? Just reconfirming. Yeah.
Correct. I've told that so many times. Why questions?
No. I was confused during
Why?
first time.
Why?
Sorry.
Where is the confusion? I don't understand. And what is
No,
the?
actually,
There should be some reason why you are confused. No.
no.
I've told so many times.
Yeah, actually, I forgot that there was a no project separately. It is only assignment. I'm very sorry for that. Just reconfirm. That's why.
Okay, see, an Excel sheet was circulated where teams had to be made and all that, right? I don't know where the confusion is. Okay, no problem. Where was I?
So one more clarification, the report or the notes on the assignments with the Jupyter notebook only, right? We need to write it. It is not any separate documentation.
Yeah, it is not a separate document. It has to be embedded with the notebook.
Thanks.
Right. And you can, all the plots, all the observations that you do has to be a part of the Jupyter notebook itself. Huh? What you submit is one file for assignment. That's all. Nothing more.
Thanks.
Okay.
Should it come as one submission per team, or in each of the team members will submit?
Submit the same thing 3 times, huh?
No, that's what I wanted to understand, sir. Like, how will the submission look?
One submission per team.
One submission per team.
Yeah.
Okay.
So unless there is, let's say that you're in a team of 3 and one person sends me a personal email saying that this person did not contribute to the assignment and all that. The rule is that everybody in the team will get the same marks for the assignment.
Got it, sir.
Okay. Yeah. So one file. Okay. So you coordinate with see, there is one other reason why I ask you to do it in teams, right? This needs some compute resource. So I recommend all of you to like buy some resource from like Google Colab or something, right? That costs some money. You can divide it amongst 3 of you or 4 of you if you make teams. Okay, so that is another reason why you should make teams. Okay, so anything else about the assignment? And I hope that the PyTorch tutorial was done the last week. Did Joas do that?
Yes, sir.
Was it useful?
Very informative, sir.
Yes, sir.
Okay. So fine then. I think now we have everything that you need, to start implementing and do the assignment. Please get started with that. Okay. Yeah. So anything else? Any other logistic thing that we need to discuss before we continue?
So one last question. So when we run the cells in the Jupyter notebook, do we need to, it has to be saved in the export, or just the code and the observations are sufficient?
You don't have to export. It's the code, the corresponding observations. See, when you write, I have asked you to plot a few things. So you have to plot them, you have to observe what you have done. And as I said, also do things that I have not asked to do or not asked for. Right. So you can do more experiments than what I have asked for, and you document that as well. Right.
Yes, sir. But yeah, the plots usually when we run the, let's say, matplotlib.plot, it generates a plot. So if the notebook gets restarted, the cells get lost for some reason, then it would be lost, right? So is it okay to, because embedding a image inside the Jupyter notebook, it increases the size of it a lot because
That's
it embeds.
okay, no? That's okay. Embedded. Means it's okay. I mean, but you have to embed.
Okay, if the results are lost, we can embed it
Yeah,
as well.
you have to embed, right? Otherwise, like, how do we evaluate? I mean, we'll not be able to run them
Okay.
again, right? We'll run some blocks for sanity check, but it's not that we can run all cells of everybody, right? So you should embed it. You should embed all that.
Okay, sir. Yeah. Thank you.
Anything else? Okay, shall we start then? Shall we resume? Sure. Hello, am I there?
Yes, sir. So
Yes,
we
sir.
can
We can
start.
start.
Okay, great. Okay, a quick recall of what we did the last time. So we were looking at the adversarial networks for generative modeling. The idea was that you are given some data, and what you need to do is transform an arbitrary random variable into like another random variable of interest, another random variable whose distribution is going to be close to the data distribution. That's the idea. Now, what did we do? We cast this as an optimization problem, which would minimize a divergence metric between the true distribution and the data distribution. So we could not, there is no way that we can compute that divergence metric because we don't know the underlying distribution. So instead of that, we created a lower bound on the divergence metric instead. So once you create that lower bound, you express that lower bound in terms of expectations over the true distribution and the generated data distribution, which can be computed using the sample estimates, right? And the lower bound that we created, okay, involves another optimization problem over a class of functions which we called as t of x, right? Now these class of functions we represented them as another neural network, okay, tw of x, and therefore you have like two neural networks, one that is representing the transformation of the random variable, okay, which would generate the data. The other neural network that would approximate this t function, which construct the lower bound on the divergence that we are working with. Okay. Then what happened is that the lower bound or the so-called cost function will have the difference between these two expectations. The first expectation is with respect to first expectation is of first expectation is on t of x with respect to px for the real data. The second expectation is of f star of t of x and the x cap or this the data expectation is over the generated data. Okay. Now, because since the lower bound itself involves an optimization problem over uh, uh, a class of functions. So we will end up solving what is called as a saddle point problem, where you have a cost function, okay, which is a function of two variables, theta, which are the parameters of the generator network, and w, which are the parameters of the t network, okay, that would construct the lower bound on the F divergence. So we need to maximize this cost with respect to W, okay, because that is what is going to create the lower bound. And once the lower bound is created, we want to minimize that with respect to theta such that the lower bound becomes close to, or rather the F divergence is minimized, or the lower bound on the F divergence is minimized, such that the P theta, which is the generated distribution, get close to Px. Okay. This is the overall philosophy of what we are doing. And in fact, if you recall, right, I had shared that screenshot of a meme on the WhatsApp, right? I mean, it's on a serious note, that's exactly how a saddle point looks. I mean, which is like that. If you have seen that potato chips, right? The top of it is how a saddle point looks. So basically, there are the function has multiple parameters, right? So at this saddle point, what happens is if you move along one direction uh, around the saddle point, the function would increase. If you move along the other direction, okay, at that same point, the function would decrease. That is what we are seeking, okay, which is the saddle point. Okay, so any questions thus far?
Sir, here basically we want that generation neural network will take less cost, but the other neural network, which is checking the image is real or not, will take more cost.
No. Hold on. See, I never said that the other network is checking whether the image is real or not. Where did I say that?
No, I'm just checking is that the correct imagination what I am thinking.
No. First of all, when did I say that this T network is checking whether the image is correct or not?
So this is discriminator.
But I never said what that is, right? I mean, see, that is an interpretation that I'm going to like give today. See, in general, this critic network is simply a neural network that would approximate this T function that creates a lower bound on F divergence. So it's better to see it that way. Okay.
So this lower bound is not, I'm not able to imagine that.
Why? See, that's what I'm saying, right? See, do you recall this thing that we did the one class before? We actually derived that lower bound, right?
No, not in that sense. Not the derivation form.
Yeah.
Okay, I think maybe throughout this class we may get, because you are going to explain about discriminator network.
No, I see. Okay, so it's an important point which you made. See, even though I would explain like what this thing would look like, I would do it only for a special case. Right. For the general case where you can take any F divergence, this is not a classifier. You understand? See, this TW network is not a classifier if you take your F divergence to be, let's say, the chi-square distance. Okay, the interpretation that you see like all over the internet and all these blogs, etc., right? They are for a special case of this, where this I mean we took this, right, which is if you make your the F function to be corresponding to this junction channel divergence, only in that case, right, this network becomes a classifier, or rather this network can be interpreted as a classifier. Otherwise, this is simply a neural network that is trying to create a lower bound on the F divergence that we would want to minimize. Is it clear? I think it's very important to have that view that why do we have that other network? We have that other network because you have to remember the entire story, right? Our goal was, that's why I've written this. Our goal was that we need to minimize the F divergence. We cannot do that and we create a lower bound on that. Now, this lower bound involves an optimization over a class of functions T of x. And that T of x is what we are optimizing, approximating using another neural network. Is this clear? So there is, see, so far there is no, there is nothing that is trying to classify between the real images and the generated images. I've never said that. Only if you make your F divergence to be the general channel divergence, this T function, right, which would still create a lower bound on the F divergence, would take the form of a classifier, and that is when you can interpret it that way. Otherwise, this T network has no meaning, other than just creating the lower bound on the F divergence that we want to minimize. Is this clear?
Yeah, somewhat.
Why somewhat? Where is the gap?
Sir, I have gone through this the last week as well, another time, but I got this confusion to just interpret. I think with this class I may get more clarity, or maybe if there is confusion, I will ask in next class.
Okay. See, you don't have to interpret it, right? It is simply a neural network that is approximating this T function, which is creating a lower bound on the F divergence. That's all. See, one has to have this kind of a generalized view. Otherwise, see, you can't go deeper than what you see in these blogs, etc. Right? The only way to make that next level of jump is to start seeing things in an abstract way.
That's agree.
Yeah, so these 3 lines that I have written, right? You start, your goal is to minimize the F divergence between two distributions. We cannot do that, so we constructed a lower bound. Now, this lower bound that we construct involves an optimization over a class of functions T of x, and that class of functions T of x is what I am representing using a neural network. That's all.
Sir, I think the diagram which we were talking about yesterday, how does the graph look like when we do a lower bound on F divergence? I think that will help Divyang more to understand what is happening.
Which diagram? I am not sure.
Yeah, you were saying yesterday, right? We'll look through a diagram that one graph that how that minimization happen, right? Once we construct a lower bound on the discriminator network, what we get, then we plot it on a graph, and then we further try to minimize it. Yeah, that graph, theta, and I think we just
Sure. Yeah, again, right. I mean, that would be for this case where your T network can be interpreted as a classifier. See, I'll do all that today. See, that is what I'm going to do now. But as I said, in the most general case, there is a version of GAN called LS GAN, okay, least square GAN, okay, where this T network is not a classifier, that will become a regressor. So you get it. So it depends. It depends on what is the underlying F divergence that you have chosen for minimization. If you choose your F divergence to be of this particular form, then this T network can be interpreted as a classifier. You understand? Otherwise, it is simply a network, okay, or a neural network that is approximating a function T of x. And what is that T of x function? That T of x function is the function that constructs a lower bound on the F divergence that we would want to minimize. Is that all right?
Yes, sir.
Yeah, Vivek?
Okay. Yes, sir. Yeah, I was just reacting. The thing is, sir, does it make a difference if we do the minimization first and then the maximization?
No. The order does not matter, especially because you are doing it in a gradient based way, no? This thing, how do we optimize this? We optimize this using gradient based minimization, right? So it does not matter. Okay. So then what did we do after that is that we looked at one instance of this FGAN, right? Which is the naive GAN. I mean that was that you see everywhere, where the F function that that you look at will be of this form, right? U log U minus U plus 1 log U plus 1 by 2. In this case, the underlying F divergence is called the Jensen-Shannon divergence or JS divergence. So for this particular case, right, if you for this particular case, if you plug in this particular F and F star and all that, the final network, right, can be represented this way, right, where the T function, if you represent the T function as a concatenation of or rather if you break down the T function as two parts, right, one that would take the X and give you a real number, and on top of it you have a sigmoid, okay, and this sigmoid is by definition gives you a value between 0 and 1. The final loss function for this, right, looks like whatever I have written within this floor brackets. Now, in this particular case, right, you can interpret this T function as a classifier because the output of the T function, okay, is bounded between 0 and 1. Okay, so that is what it is. And then we looked at how to train this this particular network in practice. So you have this loss function j cap, which is represented as j cap theta comma w. First you sample, I mean you are given n points from the data, and you are given m points from p theta as well, right? How do you get those m points? You just sample m points from the normal distribution and pass them through g theta of z to obtain these m points. And then I also showed you how to compute, right, the gradients for both these networks and backpropagate through them and train it. Okay, I don't go through this again because we did it in detail. Yeah, if you have any questions this far, I'll take some questions and then we'll move on to today's content. Any questions on this? Yeah, Rajagopal.
Hi, sir. Good morning.
Yeah.
Can you scroll a little to the top where we instantiate the Jensen-Shannon divergence as a special case of GAN? Yeah. So, sir, here this expression J theta comma W, we have here two terms. One is the expectation over Px and one is an expectation over P theta.
Correct.
So, below that you said like once we put in the values of f and f star, we get the expression which has log of dw of x and the other term. My question was, sir, how did twx change to log of dwx? Because if you're just putting the values of f and f, I understand in the ts session this might be a little more clear. Just to get some I wanted to understand how does putting f and f star values result in this changing to a log?
No, see, f has a u log u minus u plus 1 log u plus 1 by 2, right?
Yeah.
So f star for this case has a log term there.
Yes.
Okay. And you have f star of tw of x, right? So there will be a log term there that will come up.
Yes, sir, but that is an expectation over p theta, right? So how is it affecting a expectation over px star? That was my question.
You mean in the first case you are saying, huh? In the first term, how are you getting this log dwx?
Yes, sir.
I see. Okay. Yeah, I'll tell you. I think I did this algebra in the last iteration, I think. Just give me a minute, I'll tell you that. Yeah. So what we did is that, see, you represent this t function, right? The t function as, see, you look at this, right? So how are d and t related? So d is the sigmoid of tw of x, isn't it?
Yeah.
So now if you want to represent t in terms of d, what do? The inverse of that e power, yeah. So that's where you have that log. That's where you get that log from.
All right, sir. Yeah, sure. That explains it. Thank you, sir.
Okay.
Sir,
Yeah.
can you
So
please repeat that?
he was asking, the question was that there is a TW term here, right? How did you get this log DW term? Right? When it just there is no F here, how did you get this log DW term? See, how are this D and T related? See, again, see the reason it looks a little complicated here is that the GAN people just wrote down this loss function in terms of one network called DW. Okay. Now, in the terminology that we developed in this, according to the GAN terminology, what GAN people have called as DW is simply the sigmoid of our T function. It is simply a fixed sigmoid of the T function. Now, there is T here, right? Now, if you want to write it in terms of T, how are T and D related?
By the sigmoid relation.
By a sigmoid, right? Which involves a negative exponentiation. So if you want to write T in terms of D, then there will be a logarithm, right?
Yes, sir.
That's all. So you have to invert the sigmoid basically. If you invert that sigmoid, T will be written in terms of log of D. That's all.
Okay. And
So
sir, in the above term,
actually you can do, yeah, tell me.
in the above term, we are doing f star of TW of x hat. So
Correct.
basically, we are replacing u in the divergence function with TW of x hat. Correct?
Correct.
And then we are trying to simplify like replacing TW with D as we are mentioned before using the sigmoid relation.
Correct. So if you complete that algebra, you will get this expression. And if I have to do that algebra, it will take me 30 minutes. Not worth it. It's simply
Understood.
algebra, that's all. Yeah.
Understood.
Is this all right now? Okay, and I suppose that this training part, right? The forward pass, backward pass, everything for both these networks are okay. Any questions on this? Like how do you train these? Because this is exactly what I've asked you to implement in your assignments. So I hope that these are clear. Okay, so if it's clear, then we will go to start with the next. Okay, so today's agenda is that I will talk further about the GANs and the naive interpretation of how can you interpret it for this particular case. Okay, and then we will look at like a couple of applications of adversarial optimization for this task called domain adaptation and like image to image translation. Okay, there are multiple applications of GANs. I'll talk about it, but we'll look at two applications. And then if there is time, we will start the variation autoencoder part also today. Okay, that is what it is. Okay, let's start. So let's start with interpreting. Naive GAN. As classifiers. Classifier guided generator training. Okay, so this is simply interpreting the naive GAN, right? Which is with the Jensen channel divergence as a classifier guided generative model. Okay, what do I mean by that? Okay, let us recall that what are our setting. So setting is that we have data points coming from Px. Okay, we have this particular setup. Where we have a neural network of some function that would transform a Gaussian random variable to some other random variable, which is random variable of interest p theta, right? Now, let's say that what is our goal? Remember that our goal is to make p theta close to px, right? This is what our goal is. Okay. Now, suppose that there is a classifier. There's a classifier, okay, which is this. Let's call that as dw of is equal to 1 if x comes from px. It is 0 if okay, I should actually make it. Okay, not condition. Use notation dw x or x naught. So it will take either x or x cap. Okay, if it's 1 if x is coming from x cap, or it's then it is 0 if it is coming from p theta. So you understand what we are doing? So there is a classifier, okay, a binary classifier.
Sir, what about the other cases when x is not coming from px or x hat is not coming from p theta?
Come again?
Sir, we are saying that this classifier will be 1 if x comes from px, right?
Correct.
What if
Correct.
x does not comes from px?
That's all. No, it'll give 0. See, this classifier takes either x or x cap as input. Okay, and it will give you 1 if x is from px. It will give you x cap if it comes from p theta.
It will give us 0 if x cap comes from p theta.
Correct.
No, what if x or x cap which we have drawn does not come from px or p theta? Like,
No, it
I'm
should
talking
either come from px or from p theta, right? Because dw is, yeah, dw has been set up in such a way that it either takes x as input or it takes x cap as input, right?
Okay. Okay.
So it's basically, what is this? This is a binary classifier, okay, between samples of px and p theta.
Okay.
This is all right. Yeah, it's actually a binary classifier that would classify between the samples of px and p theta. Is that okay?
Yes, sir.
That's fine, right? Okay. Now here is the question. Here is a question. So
What are you eating?
yeah. Yeah, this reminds me of something, just a slight off-topic thing. See, the reason I erased it off is because if you look at the way I have written, no, it is all the letters like are not aligned along a straight line, correct? That's why I erased it off. I wanted to write it again. I remember, so like 3, 4 days back, I have a daughter, school-going daughter. Okay, so she's 8 years old. She was writing something on a sheet of paper, and she was not writing it along a straight line. And I told her, no, this is not the way to write it. So I just reminded that to myself and said, oh, if I have to tell somebody to do something, I'll have to first adhere to that. So yeah, so writing along a straight line when you don't have ruled thing is a skill. Anyway, if my daughter sees that, she'll ask me, right? I mean, you asked me to write along a straight line, and what are you doing? Yeah, so that reminds me of another joke. So I told her that she asked me, what is that you teach? So I told her that I teach math. So then she asked me to like show me what I write. Okay. So I just showed her. One day I had like taught backpropagation and filled the board with a lot of these equations of backpropagation, derivatives and all that. She looks at that picture and the question she asks is, you tell me that you teach maths, but all that you have written is English, right? So there is no math here. There are no numbers. So everything that you have written is English here. There is no math. Okay. So anyway, so the question that we should ask now is, can this classifier be used, okay, to tweak theta, okay, such that p theta becomes close to px? This is the question that we will ask now. So let's say that I'll write that classifier here. Let's say that we have this classifier. DW. So this will take x or x cap as input, okay, and gives you a number between 0 and 1. Okay. Now the question that we are asking is, can this classifier be used to tweak theta, okay, such that p theta becomes close to px? Do you appreciate the question? Did all of you understand the question? Okay. Can somebody answer that question? So now I have given you a classifier, okay, which would tell you whether this the output of this, or rather, it will tell you whether the sample that it is seeing is from px or p theta. Now I have to tweak theta, okay, by using this classifier in such a way that the distribution p theta becomes close to px. Can this be done? Can somebody answer that? Can somebody think of a way to do that?
Yes, so that is the way we do it, right? Like we train both the classifier and the discriminator.
No, no, no. I have.
No, not
see.
okay. Sorry. Okay.
I've never
Yeah,
told you
so
that story.
the
See, for
F divergence.
yeah, as far as we have seen it now, we are simply constructing lower bounds on F divergence and minimizing them. That's all. Now the question that I'm asking is, forget about everything that we have done so far, right? I'm simply asking you whether in this setup, right, where there is a neural network that would take the samples from arbitrary distribution and giving you some other distribution. I've given you a classifier that would classify between the samples of true data and the output of this neural network. Now the question is, by using this classifier, can you make your g theta such that whatever it outputs is close to px? That is the question. Now don't think about f divergence now for a while. Okay, Sanchit? I think please raise your hands virtually, because otherwise it will become sort of chaos. Sanchit, you wanted to say something?
Yes, sir. So if the samples are drawn from X, we will get a 1. But if x hat is like drawn, then we will get a 0. So what we can do is we can try to maximize the overall, like we can go for a cumulative sum of DW outputs and try to maximize that. Like,
why maximize with respect to what? See, what are you tweaking here, by the way?
sir, like what I'm like trying to see
No, no,
is
no,
like,
no, no. I'm not asking you what are you trying to say. The question that I'm asking is what handle do we have here? What is that we can tweak? See, we can tweak theta, nothing else. The classifier is fixed. Okay, so what we need to do is simply use this classifier to tweak theta. You understand?
okay.
I'm asking you a philosophical question at a very high level. How do you use this classifier to tweak this theta such that your p theta goes close to px? Is what I'm asking. Yeah, Divyang?
Sir, somehow can we use back propagation? I don't know how we can, but is it help us?
Yeah, of course. See, whenever we try neural networks, we always use back propagation. That is, see, I don't go to details. Now, details we will work out. I'm just asking you at a philosophical level. So now that I've given you a classifier, I want you to use this classifier to tweak theta such that your p theta becomes close to px. That is all. Think about it, no? Yeah, Abhitosh?
I think if the classifier has already approximated px during the classification training, then you can use the classifier to actually provide back inputs for the generator. For
What do
back
you mean by
propagation.
that? What do you mean by, see, again, don't think of back propagation, nothing, right? I mean, just
Yeah,
think of it at a philosophical level. I just want you to tell me how to use this classifier to tweak theta. Okay, let me maybe answer because it takes more time. I'm sorry, others. Okay, so
yeah.
what I would do is I would tweak theta. Okay, let me write that down. So to answer to that is that keep changing theta, right, till the classifier fails. Okay. So what is that? What do I mean by that? So what I do is I will take a theta, okay, and I will see the performance of the classifier. Now classifier is doing pretty well. Okay. So then it's not useful for me. What I do is I keep changing theta till such a point, okay, where my classifier completely fails. You understand? Now, when would my classifier fail? So now the next question is, this implies that if the classifier fail, okay, then, okay, then p theta is actually equal to px. That's my claim. Do you agree with that? See, if this classifier cannot distinguish between the samples of px and p theta, when would that happen? That would happen only when px is equal to p theta, isn't it? Do you understand? Right?
Yes, sir.
The classifier would fail only if px is equal to p theta. So now what I'll just simply use that. I'll invert this logic and say that, okay, now if I have a classifier that would classify between the samples of px and p theta, I would keep trying or rather tweaking my theta, okay, till a point where my classifier starts failing. Do you understand this?
Yes, sir.
Okay, so this is how, like, a lot of these blog posts, etc., would motivate GANs. Okay, they'll say that, oh, there's a classifier and you want to make the classifier fail because only when the classifier fails, then your p theta will go close to px, will be exactly equal to px. Okay, but there is a catch here. I'll tell you what the catch is. Yeah, I think there are some questions. Raghavendra?
Yes, are we saying that at this stage the classifier is perfect, that is able to distinguish between X or X naught? all the time.
What stage? At what stage?
So now, I mean, with this assumption that the classifier is able to do that, right? So are we already saying that it is perfect at doing it?
When we start, right? I mean, we are assuming that okay, the classifier is able to classify.
Okay.
Right? But the argument that I'm going to give you in a while will tell you that it is not enough if you just make the classifier fail. See, this thing that I said, no, that if the classifier fails, then p theta equal to px, right, is not completely true. Okay, I don't know if you can see that failure case already, but I'll show you that. I'll show you that in a while. But yeah, any other questions, Sanchit? Yeah.
Sir, I'm not sure if you are going to cover this question ahead, but just asking. So tweaking the theta randomly, it will take like really long time. So don't we have some parameter that will govern or that will tell us, okay, in which direction we have to tweak theta?
Yeah, that is correct. That is correct. But yeah, we'll see how to do that. Yeah,
okay.
It'll see the direction now is simply that it should be in such a way that the p theta should be close to equal should be close to px. That is the direction that we are talking about. Anyway, so now I mean, if all of you are convinced that if the classifier fails that p theta equal to px, this may not be true always. I'll tell you why. Huh? However, okay, classifier failures. Okay, classifier failing. Okay. Need not imply p theta is equal to px. Okay, I'll show you a counter example for this. Okay, so let's say that our features are in 2 dimensions. Okay, the data is in 2 dimensions. Let's say that my true data is like this. This is clustered somewhere here. This is only for representations. Okay, so this is samples from px. Okay, now let's say that when we start arbitrarily with some g theta, okay, I will have data, or rather p theta x cap. This is my x cap. Okay, x cap is now sampled from p theta. Okay, now let's say that there exists a classifier that would classify between them. This is the decision boundary. This is my dw. Okay. Now, okay. So first of all, please note that in practice, neither px nor p theta would be nicely clustered like this, and they are not linearly separable. Okay. So I'm simply, this is for illustration purpose. I'm assuming that they are linearly separable and there exists a linear decision boundary between them. Okay. But it may not be the case. Okay. Now, what are we saying? That we have to change theta such that the classifier fails, correct? Is that okay? Now, what is the decision that this classifier is making? So above the line px, below the line p theta, correct? This is the way the classifier is classifying. So do you agree? Whatever this above and below means. Okay, this is what the classifier has learned. Now this has to fail. What do I do? So I want to tweak my p theta such that the classifier fails. No, what I will do is I will just move this here. Let me call this as p theta 1, and this is x cap coming from p theta 2. Okay, now here dw would fail. Do you agree? Does all of you agree that dw would fail here?
Yes.
Sushil? Yeah, but now DW has failed, but has it ensured that P theta 2 is equal to Px? P
No,
theta
sir.
2 is
No.
not equal to Px. You see that, right? So now, I mean, it's not enough if you simply make the classifier fail. The classifier can fail, right? Not only when P theta is equal to Px. Of course, when P theta is equal to Px, classifier would obviously fail. However, if classifier fails, that does not imply that P theta of x, P theta is Px. Do you see that? Now this implies that P theta equal to Px, okay, implies classifier failing. Okay, but classifier failure does not imply P theta being equal to Px. Is this clear? Any questions on this, Indrajit?
Yeah, when you're moving x hat above the line, will discriminator not adjust the line to again differentiate between these two?
Good question. We have not done that yet, right? Have we done that?
No, but discriminator will do, na?
No. We have said the classifier is fixed here, right? And by the way, I have not used the word discriminator. I'm simply saying it's a classifier. So when I told this in the first class, that, please use the terminologies and the names that I've been using. I mean, I understand that it is difficult because you already know all this, right, from other sources, but it's good to use because there's a reason why I'm using those names. Huh? For now, this is a classifier, okay? So classifier is fixed. I'm not changing the classifier. Okay. Now if the classifier is fixed, then simply moving theta such that the classifier fails does not suffice, does not serve our purpose.
Yeah, but when you say classifier is fixed, do you mean this line is fixed? Because
Exactly.
otherwise he will try to classify when he has
Correct.
simple different samples.
This line is fixed. I don't know who he is. Yeah, but yeah, so classifier is fixed. When I say classifier is fixed, this of course this is the classifier that I'm talking about. It is fixed. Okay. Harish.
Sir, one question. So our goal is to make p theta equal to px, right?
Correct.
So
correct.
In that case, why do we need a classifier, for example? So we can just use a regression problem to find the loss and just use the generator, right?
No, what do you regress over? See, what do you regress over? X cap comes, right? Do you match every X cap to some X? Is that what you do? So what are you suggesting that I'll just make this, take a squared error loss and then minimize this? See, if I do this, then what will happen is this neural network would simply generate whatever is there in your data. It will not generate anything new. So you want to do it at a distributional level, no? That's why we are doing all this. Yeah.
So we need to understand the distribution rather than just using the samples.
Absolutely, that has been our problem from day one, isn't it? We want it to be done at the distribution level.
Yeah, got it.
Not at sample level, right? Okay. So now the thing is, yeah, so all of you got this, right? I mean, using the classifier and try tweaking your p theta such that the classifier fails is not enough. We need to do something more. What do you think is that something more that you can do?
Maybe the discriminator should dynamically learn.
Yeah, so you move the line. What you should do is you move the line. Okay, if this line, okay, so what you do is first you make this. So this is DW1. Under this DW1, this happened. Okay, what I'll do is I will learn another line here. I'll learn another classifier. Okay, this is now my DW2. Okay, now I have to move this p theta again to ensure that this is misclassified under DW2 as well. You get it? which means that this p theta 2 now cannot go to p theta 1 place. Okay, it has to go somewhere else. So let's say that this will move somewhere here. Okay. So now the idea is, so this will become p theta 3 now. The idea is, keep moving your p theta cluster distribution, right? So till a point where these two overlaps. Now, how do you do that? You do that by tweaking this classifier, okay, all the time. Maybe I should have written this classifier in a different color. Hold on. These are our axes, and you have the first classifier, PW1, okay, and you have another classifier which is like this. This is PW2. Is that all right? You see what's happening? So basically, we are therefore, okay, the classifier, okay, has to be changed or tweaked simultaneously. Does it make sense? Now you might ask, right? So now what is the guarantee that what is the guarantee that when I keep doing this, I will ensure that my p theta is exactly overlapping on px, right? It can actually play a cat and mouse game, right? Where the classifier moves this to some place, and then the generator tries to avoid the classifier, and they keep kind of playing that game between those two, correct? You understand? So in this case, what can happen? No, this cluster moves here and then it'll come back. So then when you try in the new classifier, it will go again here and it will come back and it can keep moving around. Can all of you see that? That this moving around can happen. So that is exactly what is called as mode collapse. Okay, where the GAN training, right, is very unstable. You will actually see that when you are training. So what happens is that the so-called classifier, right, when you are training, the classifier tries to avoid the discriminator, and the discriminator, or rather the generator, and the generator tries to avoid the classifier, and it keeps happening alternatively. Now, what is actually happening underneath, under the hood is, every time you construct this classifier, right, you are creating a lower bound on the F divergence. You understand? So what do you mean by creating a lower bound on the F divergence is learning a new classifier. Now, you can see that, right? The tighter the lower bound is, the better the minimization would be, isn't it? Obviously, right? The tighter the lower bound is on F divergence, the better the minimization would be. What do you mean by creating a tighter lower bound? Is that you create a classifier that is close enough, or a very good classifier. And in this example, I've created a very degenerative case where the classifier is linear and the data is very nicely clustered. But in practice, right, you will have these points here and you will have X points here, and the classifier will be a non-linear classifier, right? So classifier will do misclassification, okay? However, the tighter the lower bound is, the better this classifier would be. That's how the translation happens, in the sense that when the case you consider the F divergence to be Jensen channel divergence, right? You can look into this as interpret this as a classifier, right? And because you can interpret it as a classifier, constructing a tighter lower bound translates to creating a classifier that is very good. Okay. Now, if your generator function has to like make that very good classifier misclassified, okay, it would better move the cluster close to px. So because if there is a perfect overlap between these two, right, Px and P theta, there is no classifier that is able to classify these two. You understand that? Do you see that? If there exists, if Px completely overlaps with P theta, then no classifier can classify between Px and P theta, right? Points from Px and P theta. Do you agree? So what would that translate to? That would translate to saying that your T function, right, or the script T function is representative enough to give you a Tx such that the lower bound that we have created on the F divergence becomes tight. There is no approximation here. The lower bound becomes exactly equal to the F divergence. Now, if it becomes exactly equal to the F divergence, then minimizing that would make Px to be equal to P theta, right? And which means in this case of junction channel divergence, there is no classifier that would classify between the points of Px and P theta. Is this clear? So constructing a lower bound is equivalent to finding this new classifier, right? Given a particular Px and P theta, constructing the lower bound on F divergence is equivalent to finding out this classifier that would classify between these two. Okay, and minimizing the lower bound is equivalent to moving this P theta in this space of data such that it will make this classifier fair.
Are you using a pointer, sir?
Unfortunately, there is no pointer in this. It would have been so nice if there is a pointer. Does anybody know if there is a pointer here?
No, sir. iPad, it's not there.
Yeah, so yeah, I'm not because I can't use a pointer. Is this clear? So before you ask your questions, right, let me just complete the story and then. So now, instead of writing F divergence and all that, right, now we can, if we have to optimize this, so I mean, write this as a cost function, right? So what we have to do is, let's say that my X is coming from Px, right? Then I want the log, like, okay, so this, let me write what I'm trying to write. So this is like formulating the cost, okay, via this interpretation. This is what I'll do now. Okay, suppose we still have the exact same setup, okay? Setup has not changed. So Z comes from normal 0, 1, and you have G theta of Z, and what you get here is X cap that comes from P theta. Okay, suppose dW, okay, is a function from X to space of 0 and 1. Okay, now let dW represent the likelihood of a sample coming from Px. Okay, this is the way I have defined dW, right? It simply gives you the likelihood of samples coming from Px. So what do we need? So whenever it comes from Px, we want it to be maximized, no? A classifier should maximize the likelihood, okay? Or let's say Px or P theta. It simply gives you the likelihood of Px or P theta. Okay. So whenever X comes from Tx, I want to maximize that likelihood under the expectation. Do you agree? So this is, I'll write a max here. So I have to maximize the likelihood of, okay, X coming from Px. This is that term. Do you agree? Let me write it as Px for a while now. Is this okay? So this term is simply maximizing the likelihood of log likelihood of x coming from Px. Is that all right? Yes, over W. Hello? Is this all right? Now, so what is log of okay, let me write this first. What is 1 minus TW of x? Yeah. What is this? This term is, what is this term?
The likelihood that it comes from the
Likelihood that
coming from
P
x
theta.
cap is not from Px. Right? Or in this case, comes from P theta. Correct? Correct? Is it okay? Now, what do we have to do? We'll have to
It's P theta, right?
no, assume that x cap is not from Px. Oh yeah, this is from P theta. Correct. Thanks. We need to maximize this as well, right? We need to maximize. Okay, I'll have to write that. This thing also. Now, when x is coming from, x cap is coming from P theta, we need to maximize this with respect to W. So this dW, which is a classifier, has to do two things. Whenever x comes from Px, it has to maximize the likelihood of x coming from Px. Whenever x is not coming from Px, or rather x cap is coming from P theta, it needs to maximize the inverse of the log likelihood, rather 1 minus the likelihood of x coming from Px. Do you see this point? So the objective for classifier training is whenever the x is coming from Px, just maximize that likelihood. Okay? And whenever x is not coming from Px, or rather it's coming from P theta, you maximize the log of 1 minus that likelihood. Right? I need to maximize this with respect to W. Is this clear to all of you?
Yes, sir.
Okay, now what do we have to do? See, now the objective for generator training. What is it? What is the objective for generator training now? Is simply invert the objective for classifier training. Because why do we have to do that? Here the objective is to make the classifier fail, no? Now, how do we do that? If classifier is maximizing something, you just minimize that. You just completely undo whatever the classifier has done. So if I call this as some j, okay, of theta comma w, now you need to, if classifier is maximizing j theta comma w with respect to w, then generator will minimize the exact same objective with respect to theta. Therefore, the complete GAN training is that you have this j theta comma w, okay? The classifier has to maximize this while the generator has to minimize this. So again, we came into the saddle point problem. This is what you see in a lot of blog posts and the popular explanation of what GAN is, including the original GAN paper. They say that okay, we have a classifier, so we need to tweak the. This is what is called as the discriminator, right? Because it's basically a classifier. Discriminator is it just discriminates or classifies between the points from px and p theta. Okay. And now you have to tweak the classifier in such a way that px is going to go to p theta. It is not enough if you just try in the g theta, because the classifier can fail even without making px equal to p theta. So you have to try in the classifier also along with the generator alternatively. And the classifier objective is given by just maximizing. This is the cross entropy objective, right? And the generator has to invert what the discriminator is doing, and that's how you get into a saddle point problem. Okay. However, remember that this interpretation is only when you assume your F divergence to be the junction channel divergence, in which case the T network, right, that would create a lower bound on the F divergence happens to be a classifier. It can be interpreted as a classifier. Oh, sorry. Now you can see the nice connect, right? See, this objective function, right, is not some magical thing that just emerged. Okay, it had a very nice grounded mathematical interpretation where this maximization is actually creating the lower bound between the F divergence between lower bound on the F divergence between Px and P theta, right? So once you create that lower bound, you minimize that and you alternative between creating a tighter lower bound and then minimization. Okay, if you see that from, if you take one particular F divergence and interpret this dw as a classifier, in that case you can, you can write it this way, but it is not. See, this way of interpreting is not, I'm not a big fan of this because it's too hand wavy, right? I mean, yeah, I don't know, but it's just my choice. See, I would see more value and more a more principled way of understanding in saying that, oh, you start with an F divergence, you want to minimize that, and to minimize that, you don't know Px and P theta, therefore you construct a lower bound, express them as expectations over these two because you can compute them, and that lower bound happens to be an optimization over another class of neural networks. Okay, and you construct the lower bound and minimize that, and you keep alternating between these two. So that's my way of looking at it. But if you make your F divergence to be one particular F divergence called junction channel divergence, then this T function that is used to create the lower bound on the F divergence can be interpreted as a classifier, and the rest of the story follows. Okay, is that okay? It is just one other interpretation, or rather the popular interpretation of what the general case of F divergence minimization is. And again, you can see why it is called adversarial optimization, right? You have like a saddle point problem, right? Adversarial saddle point problem or adversarial optimization. Because there are two neural networks, one which is trying to undo what the other does. Okay, it is adversarial optimization. Okay, so finally, right, like post training, I'll take questions after this. Post training, I don't know if I told you this last time. Post training, inference. How do you use GAN for inference? Inference is that you take the the trained generator, throw away the discriminator completely. Discriminator is like a poor teacher, right? Once you learn from them, you just throw them away. Yeah. So then this x cap comes from p theta. Now this p theta has become close to px. In fact, there's a nice Zen saying, okay, I mean, this Buddhist Zen saying, which I hold very close to my heart, which I keep telling all my students. I don't know if I've told you this. It says that a good teacher, okay, is one who becomes redundant or useless after some time. Right? So that is the definition of a good teacher or a mentor. So you should make your mentees, right, or your students independent of yourself after some time. Now, if you keep keep your students, or you keep your subordinates or mentees for all your life, you will become a boss, right? Not a good leader or a teacher. A teacher should become useless after some time. So after this course is done, you should not be coming back to me, because uh, like you have actually got everything that you want. You have become so independent that you can do things without a teacher. My teacher told me this, right, and I'm just passing that to you. In fact, there is another nice Zen saying that says that when a student is ready, the teacher appears. Okay, when a student is really ready, the teacher disappears. It's very nice, right? It's very deep actually, right? So the goal of a teacher is to ensure that the student is ready, which is that your P theta is what the distribution that the students are in, right? And you want them to go to PX. Once you have used whatever methods, you can become like an adversary, you can scold them, do whatever, and you just invert whatever they are saying in an adversarial manner. Once they become theta star, right, go away. There is no use for you. Right? So that is what it is, right? During inference, what you do is you sample a point from Z. You get a sample from a normal distribution. Pass it to the generator, you get a sample x cap, right? That is from p theta now, which is close to px. So I mean, if you remember, I showed you that no, this person does not exist.com, right? Every time you do an inference, or rather the refresh of the page, what is happening is a sample from Z is coming, and it is going through a train generator, and a new sample is getting generated from PX. Okay, so now ideally, right, X cap, okay, is not in D. Okay, the data set that you have given, no, your new generated sample will not be in X. So if you take Z1 through ZK, you will get corresponding X1 cap through XK cap. Okay, none of these, okay, are in D. So there are new samples that are not in D. That's how you do inference. This is also called generation. Okay. See, we have still not done what is called as unconditional generation. This is still, sorry, we have not done what is called as conditional generation. It is still unconditional generation, because it is not that, okay, you give a text and a corresponding image gets generated, right? It is simply an image gets generated, okay, or a data point gets generated without any conditioning. So in the next part of the class, I will talk about how to train this, or how to convert this into a conditional generator in a while. Okay, but yeah, so this is how you do inference. So we are done with training, we are done with inference. This is how you do training of a GAN and an inference. I've asked you to do both of these in your assignment. So do implement them. So one other detail, see, I have asked you to implement something called a deep convolutional GAN, okay? So abbreviated as DC GAN. What is this? A simple thing, right? So you build a neural network, right? G theta network. You start with Z, okay? That is, let's say, in some 32 dimensional space. Okay, let me write that. So you sample Z from a Gaussian distribution. Okay, and that Gaussian distribution is in some 16 dimensional space, let's say. 16 dimensional space, okay. So now you take a vector that is 16 dimensional. Okay. Then you have to go to, let's say that your data X is in some R 100 cross 100. Now, how do you convert the 16 dimensional into 100 cross 100? See, one thing that you can do is you can have 16 and then you have, let's say, 32, then you have 64, and you keep increasing the dimensions till you have like a 10,000 dimensional vector. Okay. So this is your X cap, this is your neural network G theta. And then after you get this X cap, no, then you can do a reshaping. So X cap is in R 10,000 cross 1 dimensional, right? Which is a vector. And once you get this, you reshape into 100 by 100. So that it will look like a grid of images. Okay. And you have to do the same thing for X. No, X is in 100 by 100, right? So when you send it to the discriminator, you should reshape that into 10,000 cross 1. So you reshape X into 10,000 cross 1 and you reshape X cap into 100 by 100. This is one thing that you can do. And this neural network is a multi-layer perceptron, right? Or a fully connected neural network. Okay. You have seen how to do this back propagation and all that. This is one way to do it. The other way to do it is that you start with a 16 dimensional vector. Okay. And then do what is called as transpose convolution or upsampling. Okay. Does all of you know about convolutional neural networks here, CNNs? Is there anybody who does not know about CNNs? Okay, I'll take that as an S. So assuming that all of you know about CNNs, right? So what you can do is, see what does a CNN does? A convolutional network does. It will take a grid of images like this, and you have a kernel, which is let's say 3 by 3 kernel. You place that 3 by 3 kernel on this grid, okay, and take the inner product and you get another grid, okay. So every point in this smaller grid will now become an inner product between these two and one number, and you move this 3 by 3 grid again and you get the next thing and so on, right? That is how you do it. So this is convolution. There is something called transpose convolution where you start from a lower dimensional vector, right? And then you create a grid, okay, by doing inverse of convolution. That operation is called transpose convolution. See, you can ask TAs to do it in the next TA session, okay, how to do transpose convolution. However, there is a paper called paper or a write-up called convolutional arithmetic. Okay, so please refer to that. There they have given how transpose convolution works. So if you use transpose convolutions, right, you can finally get at the final layer, right, you actually get a grid of. You can actually make it the grid of whatever size that you want. I mean, if you are using a color image, that is what I've given you. It will be like 100 cross 100 cross, like 3 channels, right? RGB. Okay. By using transpose convolutions, you can get that into a 300 cross 100 cross 3. You don't have to reshape it. And the discriminator that you have here, right, will simply become a CNN. So it will take a 100 cross 100 cross 3 vector itself, okay, and give you a number between 0 and 1. This will be a proper CNN. Okay, you can use a ResNet or whatever network that you want. Okay, so not ResNet. You can ask TS to cover this if you want, right? What is transpose convolution? And so this, if you use, instead of using multi-layer perceptrons, if you use transpose convolutions, this entire thing, no, this is what is called as a deep convolutional GAN, DC GAN, where for discriminator you are using a CNN, okay, and for the generator you are using transpose convolutions. You are not flattening them all. Okay, that's your DC GAN. Okay. Okay, so that's that. So we will take a break now, and then maybe I'll talk about the conditional GANs and some of the applications of GANs as I promised. Before that, I'll take questions on this if there are any. Ravindra?
Yeah, so 2 questions. One thing you mentioned is this classifier interpretation holds true only for this JS divergence. Why is
Correct.
that so? Why is that
Because
specific only for JS divergence?
For others, okay, for others, this will become this thing, right, will not be a classifier between 0 and 1, right? This network will give you a real number. See, it depends on, if you recall, the output of the T network should come from domain of F star, isn't it? So that domain of F star for this case will become 0 to 1. For the other cases, it will become a real number. So in which case, the output of that network will become a regressor. It will not, whatever the case might be, it's not you cannot interpret that as a classifier.
Okay, but it is still trying to distinguish, right? It is still trying to distinguish between the other cases.
No.
So how can we interpret it in that case? So what the output of the discriminator? How can you interpret that?
I understood the question. So listen to me. You cannot interpret that at all. So there is no classification that is happening. That is why I don't give this as the ultimate interpretation. Because only with Jensen and divergence this becomes a classifier. For other divergences, no, it is not a classifier. For instance, there is a paper called, as I said, LS GAN, where what is getting minimized is chi-square distance. Let me just show you my screen, and that will become maybe more apparent. Do you see my screen?
Yes.
Yeah. Look at this now. See, for different divergences, the final output activation is different. For Pearson's chi-square distance, the output activation is a linear function, so which is a regressor. You understand?
Yeah.
So only with Jensen-Shannon divergence, you have this kind of thing which is bounded between 0 and 1, which becomes a classifier. Now, if you use the KN divergence, etc., right, you just have a line, that's all. So which cannot be interpreted anyway.
Okay. Yeah, and
right?
the second question. Yeah,
See,
yeah,
hold on. The way to interpret that is, if you want to, right, it is simply a neural network that is creating a lower bound on the underlying F divergence.
Okay. Yeah, and the second question is again with respect to lowering this, or tightening this lower bound. You mentioned that the ultimate aim is not really to get back the samples which we trained, right? We want something different. So you also mentioned that the X hat that comes out is not in the D. So can we really ensure that? Or the question is, if you
it depends on how tight your lower bound is.
If it is very tight.
If it's very tight, then actually you will get to PX, which means that you will get very diverse samples.
Okay, but not the same samples as what you trained with.
No, because you are doing it at a distributional level. That's the whole point.
Okay.
The whole point is that you have made the distribution same. See, why did we even start with all this F divergence, etc.? Is that we don't want to overfit, right? Overfitting in the case of generative models is when you match the distributions exactly. Sorry, when you only match the samples, not at a distributional level.
Okay.
Now,
So even if you ensure the distributions are same, because we are doing a random sampling, you wouldn't get the same.
Absolutely.
Training points. Okay.
Yeah, random sampling is happening because your input, right? It's actually converting one random variable to the other. You are still So, but you have to ensure that the distributions are matched. So, if the lower bound that you are constructing is very weak, right? Then you will not match distribution because you have anyway minimized a very loose lower bound on the F divergence.
Okay. Yeah, understood.
That is why people say that GAN training is very difficult. One, because you are solving that saddle point optimization problem. The other thing is the lower bound that you might get might be very, very loose. If it's very loose, then if you look at that classifier interpretation, your classifier is simply trying to move it in different places without ever overlapping it with PX.
Yep.
And also, I didn't tell you last class, right? What is the stopping criteria in training this? There is actually not well-known stopping criteria for this. Okay. The only stopping criteria is when people just eyeball the quality of the images or the data that is generating. There is have some pseudo metric to generate what it is. I mean, the pseudo metric to measure the goodness of the samples, and then they use that to stop. There is no one good stopping criteria. So in
Is
the
that
next part
because
of the class,
we do not know what is the tightest bound that we can get?
exactly, and also we don't know what the underlying distribution is. No.
Okay.
Got it. See, also, no, next part of the class, I'll talk about this versus Stein's distance and FID, right? There is a score called Fisher's inception distance, which I'll talk about the next time. That is one thing that is used to monitor the goodness of the generated images. But stopping criteria is just that you eyeball the images and see the data and use some surrogate classes and just stop there.
Yeah, thank you, sir.
Okay. Yeah, Sanjay?
Sir, in this example which you had mentioned, right, where
Yeah.
we are considering this classifier DW1, DW2, DW3, why not keep the existing classifiers when going for a newer classifier? Like what I mean to say is, instead of going for this single layer perceptron method, why not for a multi-layer perceptron here? So that we have the other classifier.
I'm sorry, I didn't follow your question. Can you repeat it again?
Okay. What I'm saying is, once we move from DW1 to DW2, right? You are saying that it is likely possible that P theta 2 might take the positions of P theta 1, correct?
Correct.
Now, if we have DW1 intact and then we go for DW2.
No, there is no intact. No, we have changed the classifier.
That's what, sir. That's what I'm trying to say. If we are going for a change, right? Let's instead of going for single layer perceptron, we go for multi-layer perceptron.
No. See, multi-layer perceptron will not prohibit the decision boundary to go somewhere else, not go to the previous layer. No, that has nothing to do with single layer, multi-layer. See, multi-layer, single layer will simply tell you whether the decision boundary is, what is the range of decision boundaries that you can learn. See, there is no remembering of the previous classifier that is happening here. You are just reiterating it completely.
No, sir. What I'm saying is, we go for a multi-layer perceptron approach. Like we say that okay,
see again, please understand what a multi-layer perceptron is. A multi-layer perceptron is simply a deep neural network that has multiple layers. That's all.
Yes, sir.
So it does not mean that you are remembering something and all that here. It is simply a neural network.
Okay.
An MLP is a neural network. That's all. You understand? It is simply a multi-layer perceptron. Did you attend the tutorials?
Yes, sir.
In tutorials, they talked about multi-layer perceptrons and training them, no?
Yes, sir.
So a multi-layer perceptron is a neural network. I actually talked about a multi-layer perceptron in the last class, if you remember. What is a multi-layer perceptron? You start with take data, okay, you multiply it with W transpose X, and then you make that go through a nonlinearity. This is the first layer. The second layer is you take W2 and then you do another nonlinearity. This is second layer. This is the third layer and so on. This is an MLP. So the architecture will look like this. No, you start with this, have a fully connected network. You have W2, you have W1, then you have W2. This is an MLP, which is a deep neural network. It has nothing to do with the classifier remembering what the previous state is and all that. That is not what we are doing. Do you see the difference?
Yes, sir. I agree on that. But maybe the terminology I used was not correct. What I'm trying to say here is that
why not remember what the classifier was at the previous state, right?
Yes, sir. It might not remember, but if we go with this approach of multi-layer perceptron, then we might have a tighter bound on the
We are using multi-layer perceptron. We are using multi-layer perceptrons. We are not using the linear discriminator anyway here, right? So these are neural networks. These are deep CNNs. Even if you are using deep CNNs, see note that your data is in some very high dimensional space, and it can always go to a place where the classifier misclassifies.
Okay.
Right? So it has nothing to do with the capacity of the classifier. We are talking about data in some 10,000 dimensional space here. Okay.
Okay.
Okay. Any other question? Sarvesh?
Yes, sir. So this transpose convolution that you mentioned.
Yeah.
So for this, the input, the Z, should it also be in a grid format, or we can use 1D convolution? Is it a design decision?
Yeah. That is a design choice. People have seen both happening, but generally people take Z to be a vector, right? Not a grid. Generally.
Okay. Okay. So
So
it's
let
in
me just
general
maybe
like.
hold on. Just hold on. Let me share that show the DC GAN paper with you so that it's appreciated. And also this convolutional arithmetic also is something that I'll show you. Hold on. Okay, we are talking no convolutional arithmetic. Arithmetic. Guide to convolutional arithmetic for deep learning. Yeah, I'll show you both of them. Do you see my screen? No, not yet. Do you see my screen?
Yes, sir.
This is that convolutional arithmetic thing. Okay. So have a look at it. They talk about all kinds of convolutions with striding, without striding, zero padding, without zero padding. They have pooling arithmetic. You see there is transpose convolution here. Okay, so please have a look at this. Okay, this is one thing. The other thing is this. Where was that? PC GAN paper. This is the PC GAN paper. Yeah, this is how they do it. So at 100 dimensional Z, and then you reshape, and then you have transpose convolutions, and then you get to 64 cross 64 cross 3. Start with a 100 dimensional uniform distribution. Z is projected. You got it, no?
Yeah. So vector only is converted into
Start from
2D
vector, and
representations
then
in the
you
at a
do
layer.
correct. Then you do upsampling, transpose convolutions, and then get to the final image dimensions.
Okay. Thank you.
Okay. Anything else?
Sir, can you please share these documents which you were presenting?
Only the
On
names. We can't type anything here. Yeah. Nothing. Okay, done. Okay, let's take a break. No, it is 11:05. No, let's come back at 11:20. Okay, and yeah, continue from here. Okay, see you in about 15 minutes. Hello all.
Hello, sir.
Yeah, you can hear me. Can you see my screen?
No,
No,
sir.
sir. So which one should I show? This one. Share screen. Start broadcast. Shall we resume?
Yes, sir.
Yes.
Yes, sir.
No, you can see my screen, I suppose, right?
Sir, one correction in the note. That's the P theta. It's missing instead of mention as P. It's before the objective for classifier training, right? That was
Come again. Where is this?
before the objective for classifier training. Before that likelihood that extra before that line. Before that. Can you go above a little? Yeah, here it's mentioned comes from P. You mentioned the P theta, right?
Okay. Yeah, correct. Thanks. Okay, shall we continue? So if we look at some of the, see, there are, after this GAN thing came, too many improvisations over it, a lot of papers, a lot of applications and all that. So in the interest of time, I'll only cover a few of it, a few of them. I mean, nevertheless, GAN is now not the state of the art for like generative modeling, right? I mean, people have moved to diffusion models and so on. But anyway, so I will cover a few of them, and rest you can read with this kind of a background. The first thing that we will do is what is called as the conditional GAN. Okay. Conditional GAN. Okay. What is the objective here? The data is given like this. So you have samples like this, x1 comma y1, x2 comma y2, and so on. Sorry, it's not small letter, it's capital x1 comma yn. Okay, so you have data this way where I'll tell you what this y is. Okay, so this coming from, let's say, p x y, some distribution. Now the x example can be like this. X can be, let's say, images. Okay. Now y can be class labels. Can be class labels or some textual embeddings. So we will actually make this idea a little more concrete when we go to text condition diffusion models and all that. But yeah, so for now, let us say that these are textual embeddings for X. Now, it's class labels for X, right? Or textual embeddings for X. And if you have data like this, the objective is to sample or generate from the conditional distribution. Just P of X given Y. So this means that there is, you will to get X given Y equal to, let's say, some class or some text. Okay, so this is class conditional generation, right? Given a particular text or a prompt or a class label, you need to generate the corresponding image. How do you do this is the question. Okay, so we are doing. So now to do it is, the problem is now the model, okay, P of X given Y, okay, instead of px, okay, using p theta. So now the thing is, the setup is exactly the same. So you have this d theta of z, okay. Now you have this x cap, okay. Now this takes z it shows some working offline. Is my screen still visible?
Yes, sir.
Yes, sir.
Yes.
Okay. Now you need
Yes,
to
sir.
generate from like px given y, right? So what you need to do first is that you condition this generation, okay, with y. Now how do you do that is that just add y as another input here. So y goes as another input to this. Okay. Now what happens is that you need to the p function, okay, or the discriminator has to classify between samples of px given y, okay, and px cap given y. Of course, there is dependence on theta. Okay, now this is now sampled from px cap given y. So now how do you do that is that for the same T network that you have, okay, the discriminator network, TW of x, right? This network, what you do is simply you have this x or x cap that is going on as input anyway. No, you add additional y as input to this. That's all. That's all it is. Now everything else remains the same. So now the cost, which is j theta comma w, right, will look like this. So now expected value of log of dw. Okay, so this dw now takes x and y both as input. The expectation is now with respect to x given y sampled from px given y. Okay, plus that other term which is expectation of 1 minus, what was that term? Log of 1 minus, right? Or 1 minus tw of x cap comma y, okay, where yeah, I can actually say that x and y comes from this. Yeah, so x and y are coming from this, and we have x cap comma y coming from p x cap given y condition of theta. That's all. So this is a conditional GAN. Now during inference, right, or inference post training, so what you do is that you take t theta, g theta star of c, okay. Now sample a z from normal 0, 1, okay, and you give a class label or text embedding as input, which is your y, okay, and generate x given y equal to some class label or text embedding. That's all. Now this y, right, can be represented as a one-hot vector. So if it's a class, okay, now it can be represented as some embedding vector. If it's a text. So basically, there are these embedding vectors, TF, IDF, or like, some BERT embedding or something. Don't worry about this. So basically, you represent a text as some sort of a vector, right? We'll talk about all this BERT embedding, how do you generate all this later in the course anyway. But yeah, so it's some vector that is representing a label. Just give that as an input to both the generator and the discriminator and solve the same optimization problem. And post training, you just take that and give it as an input to the train generator, and this will do what is called as conditional generation. Let me just show you some examples of this. It's also called CGAN or conditional GAN. You see my screen?
Yes. Yes, sir.
See this, right? This is exactly what I had written here. X given Y, and you have like they write it as Z given Y. I mean, it's basically G generator network takes Z, right? And given Y. That's what it means. So what happens in terms of network, you have Z, you concatenate Y to that and give it as an input. And a discriminator, it takes both X and Y concatenated together. Okay. Now look at the results, right? So this is for MNest. So MNest is our generated data. Every row corresponds to one particular digit. So they have conditioned it on the class labels. Okay. And yeah, so they have again conditioned it on text. This was a very old paper, 2015 paper. So they are the 14 paper, right? The embeddings were not, textual embeddings were not that great there. So this they have done class conditional generation for MNest. And I think in your assignment, I have also asked you to do a class conditional generation for the data set that I have given. Okay, so that is about CGAN. Okay, any questions on this? Yeah, Sanjit Agarwal.
Sir, yeah, sir, here X is just limited to images, or it can be
No,
some.
it can be anything. See, I've been telling this from class one, right? GANs are not restricted to images. It can be like speech. People have done text to speech using GANs. No, that is some of these models. So condition it on text and generate speech. So that can be done as well.
Okay, like
Can
we
you
have the
share the
text,
screen?
like we have the transformer algorithms, right? Like where we give a prompt of text and
No,
like
that is not, see, that is not adversarially trained. Those are uh, autoregressive models. Okay, so GPT, etc., are autoregressive models. We will talk about that as well later in the
this is
course. We will
different from
talk
that.
about this is not, see, this is adversarial learner. This is a GAN. This is not an autoregressive model. This is not a GPT.
Okay.
So this is text conditional generation of images, right? I mean, it's a GAN that is trained, which is minimizing the underlying F divergence. Is that okay?
Okay, sir.
Okay, one other question by Karthik Kumar.
Yes, sir. I just wanted to know about why. While we training, why is it like a range of values in the sense that we will give all the classes that it need to. For example, if it is class labels, we will give all the classes to which it need to train itself, so that during inference we will be giving one among that class. So why would what would be the range of why? I mean, like how from what?
I did not understand your question.
So, for example, if we are training the case of images, right, and we are giving a next prompt as you shown in the video, like in the paper, that okay, find the mountains in it or something in that sense. That can be y, right? Is my understanding there correct?
No, see why? Okay, so for now, let's say that it's class label.
Huh.
It is simply a class label, no?
Okay, so it can be something like, is it a human or is it an animal?
Yeah, represent that as a one-hot vector. So you know what one-hot representation means, right?
Yeah.
So if it's MNIST, you have 10 classes. Represent that as a 10-dimensional like binary vector with 1 zeros, right? So whenever you get from the class 1, then you give like 1 0 0 0 0 concatenate that. Otherwise you get 0 1 0 0 0 concatenate that and so on. Does it make sense?
Got it. Yeah. Yeah. Okay. Thanks.
Okay. Vivek?
So one question. So when we are okay, suppose so this is something like BERT embedding could also have been some clip embedding or some such text embedding here. But my question is, how do we join this X?
Concatenate. Make them like vectors. Just concatenate that with X and then give it as an input.
Okay, I'm sorry, that was the same question. Thank you, sir.
Yeah. So for the discriminator, you're saying now, how do we concatenate that with X?
Yeah.
Just
Because,
concatenate that. Yeah. Just
we have
concatenate
cross.
that. You flatten that and concatenate
attention
or
okay.
no attention. See, y is a vector. Why do you have attention or anything? See, y is a vector. Given a text, it is a vector that corresponds to a text. Take that and concatenate with your X. That's all. What is the difficulty?
Okay.
See, it's a vector, right? Given a text, you get a vector. All these word will give you a vector for its sentence, isn't it?
Yes.
So take that.
But it comes from a completely different vector space.
How does it matter? How does it matter? I just want pairs of images and vectors for my training. So look at this. No, what I am given is pairs of images and vectors. If I have
so your
pairs of
screen is not visible.
Is it? Okay, so basically I have pairs of images and vectors, right? And those vectors can be anything. They can come from like some embedding, or it can be one hot vector for class labels. It can be anything.
Okay.
Okay, Sushil?
Okay.
Sir, when we concatenate, do we have the same dimension size for text embedding and the image in?
No, definitely not. See, then how would you see concatenation can be done in many ways, no? See, you add one more channel for your image, right? And just repeat all this so many times.
Oh, okay. This is just a discriminator network. We are not generating anything here. Yeah. So maybe concatenation is sufficient to do that.
Correct. We are not generating Y. We are not generating embeddings. We're just using embeddings to generate from X conditionally.
Okay.
Given a text or given a one hot vector, we want to generate from it. We are not generating embeddings here. There is no attention, nothing. I mean, it's simply taking a vector corresponding to a text. You don't even have to do BERT. Okay, sorry. Maybe I wrote this and you got confused. See, embedding can come from anything. No, let's say that it is simply a take TF-IDF. Okay. You understood, right? I mean, it is some vector corresponding to this vector. With this thing, you concatenate that. You have a pair of data or image and vector. You concatenate that vector with this and then try the CGAN. Nothing complicated at all.
Okay.
But sir, what is the difference between the CGAN and normal GANs that we use?
Nothing. The GAN cannot do conditional generation. Conditional GAN can do conditional generation. See, in a normal GAN, right? Suppose you build a normal GAN on MNIST. You can't control what digit you generate when you do inference. Here you can control what digit you generate during inference.
Okay. Yeah, okay, sir.
Is that all right?
Yeah, thank you, sir.
In fact, in the data set that I have given you, there are some 90 classes, different animal faces, okay? So now I've asked you to build a CGAN on say 20 class, there's some 10 or 20 subclass of this data set. So what you will see is that when you give that particular, the way you should do it, to take those 10 classes, represent them as one hot vectors like this, 0, 0, 0, 1, wherever the class is, concatenate this with the Z vector, okay, and give that as an input to your generator and also the discriminator. During inference, when you concatenate, this is like a switch. So whatever class you want, you take that particular class and it will generate. Do you understand that?
Yes, it is the headache of the backpropagation to find out what, in which ways these vectors have to be combined and the image has to be generated.
Yeah. See, don't say it that way. See, the thing is, remember what we are doing. We are trying to minimize the distributional divergence. See, if we do it well, then the divergence between Px given y and P of Px cap given y and Px given y will be minimized. No. What do you mean by that? I mean, that is why I spent 2 full classes on trying to make you appreciate what does it mean to minimize distributions.
No, the reason why we concatenate is what I was talking about. So the if we concatenate also, or maybe if we do some complicated thing like some cross attention or some such neural
just
cognitive
add if you
neural
want.
network.
If you want, you can add. No problem.
Yeah. Okay. So
you can combine them any way you want. Any way you want.
Okay. Yeah. Yes.
Okay. Shall we move on?
Yes.
Okay. So we'll go to one other application of this. The next thing that we will do is. So we already saw, right, that we can do conditional generation. And one other advantage of doing conditional generation is that suppose you are solving a classification problem, okay, and you have less data. What you can do is you can build a GAN, a conditional GAN, okay, and generate class-specific data using conditional GANs and use that for augmenting your classifier. You understand? So if you can do a class conditional generation, then you can use that to augment your classifier for your downstream task. Does that make sense?
Sir, please repeat again.
Suppose you have a classifier, okay, and you want to train a classifier, and you don't have data from one of the classes. What you do is you build a GAN on that data, okay, the conditional GAN, and generate more data from that conditional GAN. So if you do it in an unconditional way, what happens is you will not know what the label of the generated data is. If you build a conditional GAN, you already know what label the data is coming from, right? And you can use that to augment your classifier and retrain your classifier with more data.
Yeah, correct, sir, correct.
Aditya?
Sir, but the GAN generated images, wouldn't it basically already be able to, so the second half of the GAN anyway can, so wouldn't it, like my doubt was the data set, the amount of information we have in the images, we are just creating instances of that, right? So the classifier should be
No,
able to learn the same amount
no,
from the
no. You will generate new data, right? It's like augmenting your data. Suppose you have more data in your data set, the classifier would anyway become better.
Okay.
Right? I mean, again, this is under the assumption that you have trained your GAN well so that the underlying distribution is correctly estimated. If it's not estimated, then what you're saying is true. I mean, then classifier will only see some noise. But if the underlying distribution has been correctly estimated via GAN training, good GAN training, not only GAN, you can use it for any kind of classifier, I mean, any kind of generative model, right? Take a generative model, train it well, and you can use that data. Of course, you need to do it in a conditional way. Use that data, augment your classifier. You can always do that.
Okay, so my doubt was if we had sufficient images in order to actually generate the actual distribution required of that images, then wouldn't that be sufficient to directly give a good classifier, because we have enough to even estimate?
Not necessarily, not necessarily. But I mean, your question is valid. What you're saying is, if we can anyway estimate the underlying distribution, would classifier would anyway do that? No, not necessarily.
Exactly.
Sometimes what you're saying is true in a sense, but sometimes what happens is let's say that your classifier is restrictive in the sense that you can't make your classifier large enough, right? In that case, even if you have a lot of data, because of restrictions on the architecture of the classifier, unless you have more diverse data, you can't train the classifier well.
Okay.
Right? So in those cases, you can, or the other thing that you can do is, let's say that you have class imbalance, right? Then to sample from the tail of the distribution, you can use conditional GANs and then augment your classifier.
Understood. Okay, sir.
Yeah. That's a good question, by the way. Yeah. Sachin?
Hi, sir. So the original data must have some data from a class, right? The generator cannot.
Of course. Otherwise, you can't do a conditional generation, right? Yeah. It should have some data from all classes. Yeah. Or rather, the class that you would want to sample from. Okay. So let's move on. So I'll talk about two applications of GANs, and then we will move to the next topic in the next class. The first thing that I want to talk about is what is called as image to image translation. Okay. Image to image translation. Okay, what is the thing here is, the objective here is, let's say that we have two data sets. X1 through Xn given by, let's say, Px, and there is Y is not, what do we call it? Set is also taken. Okay, let me change the notation. S1, S2 to Sn, some data that is coming from some distribution PS, and you have T1, T2, Tn that is coming from Tt. Okay, so the objective is that just a second. Show some examples so that you appreciate it better. Just opening that paper. Just a second. Now the objective is to translate. Tell you what that means. Translate from PS to PT. Okay, what does that mean? I'll simply show you an example and you will understand that easily. Do you see my screen?
Yes, sir.
Yeah, this is what it is, right? So I suppose I want to do a style transfer, meaning that I have some style image and I want to convert it to some other style. And I mean, this is another example, right? If I have zebra images, I want to convert them into horses. If I have this, these are different styles, photograph to Monet to Van Gogh paintings, etc. You have winter images you want to convert into summer. There are more examples. You have, let's say that you have sketches, you want to convert that into the full images. Some other examples that are given. Yeah, this is like you have maps, or rather satellite images. You want to convert it into map, and the other way around. You have the segmentation maps. You want to convert that into full images and so on. Okay. So this is what I mean by translation. So basically, in my notation, you have been given data from two different distributions, PS and PT. The objective is to convert from one distribution to the other. Uh, did you understand the objective? Is it clear?
Yes, sir. It's clear.
Okay. Now, how do we do that? Is that so? Recall that a GAN, right? So what does it do? It'll take an arbitrary random variable and project it to random variable of interest. So this is arbitrary, right? This is data of interest. So there is no reason why Z to be arbitrary, right? So what you can do is you can build a GAN, okay, that to take data from the source distribution. So S coming from PS. And now this converts it into the T coming from PT. So let's call that T cap coming from PT cap. Okay. Now have a distribution. So what you are trying to do is you are trying to start from the source distribution, okay, and generate the target distribution. Does it make sense? You can do that, right? So basically you can start from any random variable and go to any random variable as long as, so this F divergence, okay, that you minimize the divergence between the true target distribution and the generated target distribution. Via this GAN. This you can do. Of course, there will be a discriminator here, right? Because it's a GAN that we are talking about. There is a discriminator, okay? That will take the generated image, T cap, or the real image from the target distribution T and gives you a number between 0 and 1. Now, but this will, so this entire thing, right? This thing will convert PS, right, to PT. Agree? So here, right, what is this doing? This is convert PZ to PX. Similarly, this is converting PS to PT. Do you understand this?
Yes, so in that case, G theta of S will look like a autoencoder, right?
No. Where is autoencoder here?
I mean,
simply
in the
take,
sense like
there is nothing.
there will
Please,
be a
no. There is no autoencoding. Nothing is happening, right? Simply a GAN. Instead of taking Z, it will take S as input and it will give you T cap as output. That's all.
okay.
Why
So
is there an autoencoder here?
so will there be a need to have a equal sized image? I mean, so initially we sampled Z and we got G theta of Z.
That's a different question. That's a different question. So what should be the architecture of this? Architecturally changes. Of course, you start with an equal sized input. Yeah. But there is no auto encoding. Only the size of this network changes. That I agree.
Okay.
Okay.
Yes.
Yeah. Any other questions on this?
And sir, one more thing. Sir, how we can identify or calculate the performance of this GANs? Like how it's performing well on the data?
This question does not fit into what we are discussing right now. It is a good question, but it is not. I'm talking about this image to image translation, right? Like not talked about evaluating GANs yet. So I request all of you to like ask questions that are relevant to what is being discussed right now. Okay. But I'll answer that question. How do we evaluate? I actually hinted that in the previous session. I told you that there are metrics called FID, etc., which I will describe. But yeah, any question that is like relevant to what we are discussing right now, please raise your hands before asking questions, please. Yeah, Harish.
So while sampling this distribution, the samples from PS from the distribution S here. So we really don't know the distribution, right? Underlying distribution. in this
We
case
don't
also.
know. It's just like Z. Yeah,
Yeah.
we don't know. We neither know PS nor we know PT. We just have samples from it.
So
what has
when we
been
have
given as
samples,
data?
okay. So how do we convert that to, like, for example, in the general one, the Z is of the form of like 16 or 32.
That I already told you, right? You start with it's a CNN, so it's basically a CNN, right, of the same size. If you want, I can write it this way. It's of the same size. This okay. The input and the output. I mean, the intermediate layers can be anything, but you can actually make it a unit if you want. Okay, let me just write it. It's an architecture choice. What you can do is start from PS, okay, and reduce the dimensionality and just increase the dimensionality again. And then get your P. This is from PS. This is your G theta of S. It's an architectural choice. You can do it anyway. So you can reduce the dimension and increase the dimension again to get to T. And T and S has same dimensions. Is it all right? Okay. Sushil?
Sir, to the discriminator, you have T cap or T. It should be and. If there any specific reason you're writing or.
I mean, like by or, I mean, see, when you are looking at the first term, you need to give T. When you're looking at the second term, you need to give T cap.
Okay.
Right? That is how we have been doing it, no discriminator. There are either T cap goes as input or T goes as input, depending upon what term you are evaluating. Okay. Yeah, Sarvesh?
Yes, sir. For this image to image translation, so shouldn't there be a need of a mapping from which S is mapped to which T, or like
Good
this?
question. Good question. Good question. Yeah. See, there was a paper called Pix to Pix that actually paired. I mean, this is called pairing. So now, how do you? I mean, the question that you are asking basically is that how do you ensure that one corresponding S goes to that same T, right? I mean, the example that I showed. How does the semantics get preserved? That's a very good question.
Yes,
That is why, in the first paper called Pix to Pix, okay, it's called Pix to Pix. Here there was pairing. Okay, so pairing was there, and pairing was an issue because when you get the data, you wouldn't get pairing. There was another paper that came, which was called Cycle GAN, where there was no pairing. Okay, what they do is they do this trick called what they do now. If you want to convert from S to T, okay, so they have a GAN, okay, from S to T. Okay, then they also have another GAN from T to S. Okay, now what they do is, in addition to two GAN losses, okay, cycle GAN also has
Style loss.
no, as what is called as a cycle consistency loss. Okay, cycle consistency loss. Now, what do you mean by cycle consistency loss? What they do is, so for GAN from S to T, so you have this, no? You have expectation of log of ds. The image that you get is from T, and you have T coming from PT plus that expectation of log of 1 minus ds T cap T cap coming from that generator, no? P T cap theta. Okay. In addition to this, they will have another loss. Okay, that would say that the if you take the actually, yeah. So there is another GAN here, right? Which is similar to this expectation of log of dt on S coming from PS. So they do another the other direction. They do translation in other direction also. They have this and S cap coming from PS cap. Let's call this P, right? So what they do is they'll say that if I take, I will write that maybe. So there are two generators here. So generator 1 is taking S and giving T. Let's call this G1. There is another generator. Of course, there are two discriminators also. This is taking T, okay, and it is giving you S. Now, what they say is that if I take an image, okay, that has been generated, okay, if I take G1, okay, and pass a T to it, sorry, G1 takes S, no, if I take an S and pass through it, what should I get? I'll get an image in T, correct? Now I will take this image T and pass it through G2. What should I get?
Say
Again,
S
the
S
same
prime
image,
S
S.
prime S prime.
Right, I get S, right? I should get S, so I minimize this loss. This is called cycle consistency loss. Similarly, they do this. They take G1, okay, and G2 pass through a T, you will get an S. You pass it through T, you will get another T. So take that corresponding T and manifest this. So this is what is a cycle GAN. They claim that if you do this, in addition to trying to GANs, then the pairing will happen. Let me just show you that. Is my screen visible?
Yes, sir.
Yeah, you see that, right? There are three objectives here, right? One is the two GAN objectives, of course, and there's the cycle consistency objective. What is cycle consistency objective here? So they call this T and S as X and Y, by the way. So and two generators as G and F. So when X goes through G, you get an image from Y, and then you have to go make it pass through the other generator and match that with X1, X input image. And you do this for the other generator and add that as another loss. Right? So this is what they get, no input, output of the generator, and the reconstruction that is happening. So you have to ensure that this also happens. And they show that if you do this, then I mean, you can use this for image to image translation. Okay, so that's
Got it, sir.
about the
Got it.
cycle
Thank
GAN. Let me share that. See, as I said, no, there are so many applications that GANs have been used for. And, I can teach a full course on GAN, but yeah, so we don't have that time, unfortunately. Yeah, questions, Vivek?
Sir, I'm sorry, but I did not understand the pairing that
there is no
was
pairing
the question
here.
that was asked.
There is no pairing. See, the question was, while doing this, do you need the corresponding S and Y? See, in the example that I showed, if you take a sketch and you want the corresponding field image, no, while training this GAN, do you need the pairing is the question. Meaning,
yeah, we should, right? We need.
No, we don't. That is what I'm saying. In pix-to-pix paper, pairing was needed. But in cycle GAN, pairing was taken. I mean, they gave up pairing. They said pairing is not needed. Then how do you ensure that the corresponding image gets generated is through having these two different generators. Even though you want S to be converted to T, you also have another GAN that is T from S, and then you have the cycle consistency.
Convert it back, and then the difference between them should be minimal. Okay.
Yes.
Oh, okay. Okay.
Okay. Yeah. Sanjit?
Sir, so in cycle GAN, we eventually come up with two GANs which help us to translate from S to T and the other one from T to S.
Correct.
Okay.
What's your question? You're just clarifying, is it?
Yes, sir. So I thought that the other GAN was just for learning up the first one.
You can say it that way, right? It is aiding the learning of first one, but it also gives you one additional advantage that you can have conversion back also, no T to S as well.
Okay.
Right?
Okay, sir.
Yeah. Yeah, Sachin.
Sir, so when pairing is given, it's more like conditional GAN.
It becomes like a conditional GAN. That's a good observation. Yes, it becomes like a conditional GAN. Correct. That's a good observation. Instead of having uh, like a text as a one-hot vector or as a conditioning variable, you have this image as a conditional variable. That's a good observation. Yes. In fact, you can see this, right? You can use GAN for in painting now, image in painting, because you can use the input image or the like masked image as input, and you can train a GAN to complete the image. See, you can imagine any of the applications now, because what is GAN doing at the end of the day? That is why you need to have that abstraction that's starting from arbitrary distribution, it converts it into distribution of interest. And it does that via minimizing the F divergence. Now you take your input to be anything that you want and output to be anything that you want, and imagine whatever application you want there, right?
Correct.
Yeah.
So, sir, in basically these like mobile phones and everything, we see many photo editing tools like which convert the image or enhances the image.
Yeah, they can be GANs. Yeah, they can be GANs, but right now the state of the art is not GAN. They use diffusion models as generating models, but the fundamental idea is the same. They use diffusion models because they are more easy to train and robust. We will come to diffusion models later in this course. Okay.
Thank you.
Okay. Yeah. Ankush.
Sir, when we say that S is translated to G by passing to G1, it gives you T. And in the G2, when we are passing T. So my question is, when we are passing through this, there will be like coefficient added by G1, right? It will be
What do you
converted
mean by
whole?
quotient added by G1? I don't. What do you mean by that?
Okay, so when you say that we find a loss function by passing it to G1S minus S, right? And that gives you the value of it, right? What is the loss function happening?
No, no, not loss function. Yeah, G1 of S is simply an image.
Okay.
G2 of G1 of S is another image. You're just looking at the differences of the images. See,
Yeah,
G1 is
but
a generator, no?
generator. So the image is same, which is passed, like S is same, and
It is
whatever
not.
we are
Okay,
getting is
hold
the
on,
output of.
hold on. Please hold on.
Yeah.
I'll tell you what is happening. Take an image S, pass it through G1, you get another image T, right? You
Correct.
take
Right.
that T and pass it through G2, you will get some other image S. See, that image, or maybe I should.
Okay, that's not the original state,
Why is
right?
it the original image? Why is it the original image? It is the output of the generator. It is something.
Right.
You are
That's
matching
what I
that
was
to the
confused.
original image. Yeah.
Okay, that's what I was confused. I thought you were telling like we are reversing the process and finding out the loss function after that. Like
It's simply
after
passing.
passing.
No, you understood what I'm saying, right? So it's okay. So it's a
Thanks.
different image. Yeah, it's not because it is the generator, right? You'll have actually
Yeah,
there'll be another
I will.
one discriminator here. TWS. There will be another discriminator here. Is it DWT? Yes, go on, Mukesh.
Sir, when we are talking about the differences between these two images like G2T and G1S.
Pixel level differences. Pixel level differences.
Oh, it's a pixel level.
Yes.
Okay, correct. Thank you, sir.
Okay. Yeah. Yeah,
Thank you, sir. I
Harish.
got it.
So one question. So from this, we can see that any arbitrary distribution can be converted by training to one more other distribution, right, to make it closer to the one.
Correct.
But are there any cases where we cannot do that? Like, for example, there are two distributions which we cannot train again for them to convert to one more distribution.
Theoretically, no. You can convert anything to anything. Theoretically. Yeah, practically what happens is if you do not have like strong priors on data, for instance, if you have, let's say, data like tabular data or data like, where you have compositional data and all that, now it's difficult to train GAN. But theoretically speaking, you can do it. Anything is possible.
Thank you.
Okay, I think all these questions, yeah, it's okay. I'm not discouraging that, but yeah, so time is 12:10 now. See, there is one other thing that I wanted to do, which is like domain adversarial networks. which is way to solve solve the problem of domain adaptation. Okay, via GANs. So I wanted to do that. It'll take 15 minutes. People like complain if I extend. I'll do that in the next class. Okay. I wanted to finish this and go to variational autoencoders in the next class. But anyway, so it'll take me 15 minutes. I'll do it in the next class then. Okay. Okay, that's all for today.
Thanks.
So we'll have a quiz next class, starting at 9. After the quiz, we will look at the domain adaptation with GANs, and then we'll move to VAEs. Okay.
Yeah, thanks.
Please see, what I recommend you is that now that we have come to the thick of the things, please start reading the papers that we have discussed in the class in the original. And if you have questions, you can either contact me or TAs and get your doubts cleared. Huh? Okay. See you then. See if I while asking questions, I'm just trying to moderate it a little so that there is relevance. So don't get me wrong. Huh? So yeah, questions are always encouraged. Okay, see you next week then. Bye bye.
Yeah, thank you, sir.
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 Thank you, sir. Bye.
Thank you, sir.